Welcome Physics 1 students to the Lab 8 Prelab. Today we're going to be learning about Archimedes' principle and how it relates to buoyancy force. So to start things off, let's do a little bit of a corny joke. So you can tell the gender of an ant by throwing it in the water. If it sinks, girl ant. If it floats, boy ant. So another cultural reference relating to buoyancy has to do with the Titanic. So all you really need to understand for this reference is that the movie revolves around two main characters, Jack and Rose, or Kate Winslet and Leonardo DiCaprio. They meet on the Titanic and they fall in love, but spoiler alert, the Titanic hits an iceberg and it sinks. Once it sinks, Jack and Rose find a door, that's the door right here, floating in the wreckage, and Rose survives because she's on top of the door while Jack is hanging off the door and he promptly freezes to death. And then there's this really great iconic scene where Rose realizes Jack is dead and is like, "I'll never let go, Jack. I'll never let go." And then pushes his corpse off the door and into the depths of the Atlantic Ocean. Naturally, this created quite a stir on the internet as people set off making memes like the one here, saying that the two could have fit. But another meme from another classic movie, so that's right here, The Matrix, Morpheus explains the pitfalls of this meme. So you can see here that they're showing what it was like in the movie, right? Rose on the door, Jack off the door, but showing that they could have fit if they laid side by side, or laid on top of each other, or sat there and played cards, or posed the way they're posing here. But as Morpheus says, what if I tell you it's not about space, but it is about weight? So that's what we're going to talk about today, how the mass, volume, and density of an object can cause an object to sink or float, and how this relates to the mass, density, and volume of the fluid being displaced by the object. But first, meanwhile, in Corpus Christi, there are Jack and Rose and some of our potholes. So Archimedes' principle states that the volume of a displaced fluid is equal to the volume of the submerged object. So buoyancy force, which is capital F subscript capital B, as I like to abbreviate it, is the force the displaced fluid exerts on the object, and it is equal to the mass of the fluid displaced times gravity. So essentially, it is the weight of the fluid. So buoyancy force, we can see that here, is equal to the mass of our fluid that's been displaced times gravity. So just the weight of whatever that displaced fluid is. Another way that we can write this, which is really handy depending on the information that we're given, is that the buoyancy force is equal to the density of the fluid times the volume of the fluid that's been displaced times gravity. And the reason that we can write it this way is because we know that density, which is abbreviated as the Greek letter rho. No, I don't know why it's not delta, it's rho. But we know that density is equal to mass over volume, so we know that mass is equal to density times volume, right? So that's what we've done here. So a lot of times you'll see practice problems and they'll give you the density of your fluid and the volume of your object, and so having this equation is really handy. Another way that we can do this, to expand this equation a little bit further, is to expand our volume term. So we can turn our volume term into our cross-sectional area times our depth of the object submerged. A simple example would be, say we have a rectangular object. We know that the volume is length times width times depth, and we know area, so cross-sectional area is length times width, so the volume is just going to be our cross-sectional area times the depth that the object is submerged. So just a quick little recap of all of our terms that we just went over in these equations, because we're going to be seeing these equations over and over again. M stands for the mass of the fluid displaced by the object. G is gravity, so 9.8 meters per second squared. Rho fluid, that's our density of our fluid in which the object is submerged. V is our volume of the object that is submerged, or volume of fluid displaced by the object. So this might not necessarily be the whole object. As you can see in this picture, the water line goes through about the center of the object, and we are only concerned with the part that is submerged, not the part above. The part above does not impact buoyancy force unless we apply a force to submerge it. Only the part submerged affects buoyancy force. Then A is our cross-sectional area of our object, and D is the depth up to which the object is submerged. So it is the height of the water on the object. It is not necessarily the whole height of the object. Be very careful with this point, okay? When you're doing these practice problems, a lot of students fall into that trap where they'll use the entire height, but it's an object that's floating, so the whole height isn't actually submerged. All right. So, buoyancy force versus our weight force of our object. Okay, so if the weight force of our object is greater than our buoyancy force, that means that our object is denser than the fluid, and that means that our object is going to sink, right? So if our weight force is bigger than our buoyancy force, it should come as no surprise that our net movement is going to be down until we reach to the bottom of the vessel, right? However, if our weight force is less than or equal to our buoyancy force, that means our object is less dense than the fluid, so our object is going to float. And so this is once again one of those situations where you do want to be careful about what your depth submerged is, right? Because we can see that this whole object here is not submerged, and the buoyancy force is only being calculated based on the object, the part of the object that is submerged. This is the only part of the object that is displacing the fluid, right, which is generating this buoyancy force. So another important thing to be familiar with is specific gravity. So specific gravity is what is going to allow you to figure out what the depth that the object is submerged. So what specific gravity does is it just is a ratio between two different densities. So you'll be given the density of an object and the density of water or your fluid. Okay, so you'll divide the density of your object by the density of your fluid, and that will tell you what percent of the object is submerged. So that you can think about your decimal answer being multiplied by 100 if you want to think of it in terms of percent. That's the percent your object is submerged. Or if you do the ratio and you're just straight up looking at the fraction, that's telling you the fraction of the object that is submerged. So forces and buoyancy. So just like we've been doing in many of the other labs, when we sum up our forces in our y direction for buoyancy, buoyancy is going to be upward, which I'm going to define as the positive direction. Our weight force of our object is going to be downward, so it's in the negative direction. So when we sum up our forces in the y direction, we have buoyancy force minus weight force is equal to 0. The reason for this is because this object is in static equilibrium. It's not moving vertically, it's just floating on the surface of the water. We have no applied force, so we know that the buoyancy force is equal to our weight force in this situation. Now, if we were to apply a force, so Fa, if we push it and we completely submerge it, when we sum up our forces, still maintaining that upward is the positive direction, well, we have our buoyancy force, right? That's upward, but our applied force and our weight force are downward, so minus Fg and minus Fa. Now this is equal to 0 because we're assuming that we just apply this force and then we're holding it submerged, and this object isn't moving up or down once we've applied this force. So this means that our buoyancy force is going to increase due to this applied force. That's because more volume of the object is submerged, so that means more fluid is being displaced, so that generates a greater buoyancy force. So in terms of Fb, Fg, and Fa, the buoyancy force is equal to Fg plus Fa. Now in a scenario where we push the object out of the water a little bit more, then it would be in equilibrium. So now we have an applied force going upward, along with our buoyancy force upward and our weight force downward. When we sum up our forces in the y direction, we have Fa is positive, plus Fb, which is positive, because both are upwards, minus Fg, which is negative, because it's downwards. And then this is equal to 0, because we're just one time applying this force and we're holding it out of the water. So now there's no vertical movement once Fa is applied. So the buoyancy force is going to decrease due to the applied force because now less volume of the object is submerged due to our applied force. So that means that our buoyancy force, if we rearrange this equation, is equal to the weight force of the object minus the applied force. So before we get into our pre-lab practice problems, I just wanted to mention an alt code which you might find handy as you're writing your formal lab report. This again works in Microsoft Word and PowerPoint, but unfortunately not in Excel. But in order to use this alt code, you just hold your alt key, so this guy, and you type in the numbers plus 961 on the number pad, so that's over here on the right, and then you don't have to go to symbol and insert symbol. It'll just insert your row. So here we'll do a little quick demonstration text box. So I'm going to hold my alt key and then I'm going to press plus 961 and you can see I get a row. Alrighty, so let's get started on the pre-lab practice problems for lab number 8. So the prompt says that a wooden block of 1.1 centimeters by 1.8 centimeters by 6 centimeters is floating in water. The density of water is 1,000 kilograms per meters cubed, and the density of the wooden block is 600 kilograms per meters cubed. So our first pre-lab practice problem says, what is the magnitude of the gravitational force acting on the block? So in layman's terms, we want to know what is the weight of this block. How much does this block weigh? Okay, so unfortunately, they don't tell us what the mass is. That would be really straightforward if they did. But we do know this relationship between mass, volume, and density, right? And they did give us the volume of the block, and they did give us the density of the block, right? So we can come up with a workaround to find the mass. So we know density equals mass over volume. So that means that mass is equal to density times volume, right? So in other words, if we want to solve for mass, because ultimately we want to multiply it by gravity to get the weight of the block, then we just need to take the density of the block, multiply it by the volume of the block, and that'll give us the mass of the block. So when we do that, we get 0.007128 kilograms. And then once we multiply it by gravity, so we take our mass, multiply it by 9.8 meters per second squared, we get 0.07 newtons is the weight of our block. Now, when you do these problems, I can't emphasize enough how important it is to convert to meters unless you're being specifically asked for your answer in centimeters or another unit. Remember that newtons are kilogram meters per second squared. So if you don't convert to meters and you leave it in centimeters, what you're getting at the end will not be in newtons. So please be very careful of that. If you're doing a drawing, I would highly encourage not even letting centimeters make it into your drawing, just like I've done here. But of course, just do what works best for you. So now if we move on to pre-lab practice problem number 2, which is what is the magnitude of the buoyancy force acting on the block? So now we're calculating the buoyancy force. We're going to sum up our forces in the y direction, and as you can see, I've defined upward as our positive direction, so that means our buoyancy force minus the weight force of our block is equal to 0. Since there's no vertical movement and the block is in static equilibrium, we know that it's equal to 0 because there's no net acceleration in the vertical. So this means that the buoyancy force is equal to the weight force, which means that buoyancy force with no applied force is equal to 0.07 newtons. All right, pre-lab practice problem number 3. What is the specific gravity of the block? Okay, so remember, specific gravity is just telling us what the ratio of the two densities are. So the density of the object to the density of the water. So we know that the density of our object is 600 kilograms per meters cubed. We know the density of the water is 1,000 kilograms per meters cubed. So when we divide them, we get 0.6. And essentially what this value is telling us is how much of the object is submerged, what depth the object is submerged up to. Okay, this means that 0.6 of the long side of the block is submerged. In other words, depth is equal to 0.6 times the entire height of the block, which we know to be 0.06 meters. Or you could think about it in terms of percent. 60% of the long side of the block is submerged. Which brings us to problem number 4. If the block is floating such that its long side is oriented vertically, which probably wouldn't happen in real life, but it can in physics problems, so how deep is the long side submerged in the water? So now we're finding out what this depth submerged is. And so if you're following along on the pre-lab practice problems, you could probably see that our answer is in centimeters, which is why we're going to calculate it in centimeters. So When we're finding our depth submerged, it's just going to be our specific gravity times the long side of the block, which is our entire height of our block, right? Because that's how it's oriented. So the depth submerged is 0.6 times 6 centimeters, which gives us 3.6 centimeters. That means this depth here that it's submerged is 3.6 centimeters. All right, so pre-lab practice problem number 5. What force must be applied to the block to have the block be exactly half submerged? State both the magnitude and the direction of the force. So what do we need to have the block submerged to have it be exactly half submerged? Well, we need it to be submerged 3 centimeters, right? Because the entire height of this block is 6 centimeters or 0.06 meters. So half of that would be 3 centimeters or 0.03 meters. So when we sum up our forces in the y direction and we're thinking about which way our applied force should be, we want to think about what the block would be doing if there were no applied force, right? And if there were no applied force, this block would be floating with 3.6 centimeters submerged in the water, which is more than we want, right? So we need to push the block up out of the water by 0.6 centimeters so that only 3 centimeters are submerged, right? So you can see here we have our applied force. It is acting upwards, right? So that we have only 3 centimeters submerged. So when we add up our forces in the y direction, we have our buoyancy force, which we don't know anymore because we knew what it was for the equilibrium scenario, but now only 3 centimeters are submerged. So it's going to change. It's going to decrease a little bit from our equilibrium scenario from problem 2. So it's going to be a little bit less than 0.07 newtons. We don't know our applied force. That's exactly what they want us to find in the problem. But we do know our weight force, which is nice, right? We didn't bring a beaver into the lab. It didn't start munching on our wooden block. So we still know that the weight of our block is the same. Unfortunately, one equation and 2 unknowns is a bad thing, though, so we need to bring another equation into the fold in order to solve for one of our unknowns so that we can solve for what we want to know. Okay? So the first thing that we're going to do is we're going to find out what our new buoyancy force is with less of the block submerged, which means less of the fluid displaced, which means essentially a smaller buoyancy force, right? So we know our buoyancy force is equal to the density of our fluid times the cross-sectional area of our object times the depth that the object is submerged times gravity. So when we plug those in, this is the density of our fluid. This is the cross-sectional area of our object. That hasn't changed, but the depth submerged has changed. That's what's really important to remember here. We want it exactly half submerged, so our depth submerged is 0.03 meters, so 3 centimeters, times gravity, 9.8 meters per second squared, and we get 0.0583 newtons, which does make logical sense with what we said before, that it should be smaller than our equilibrium scenario when more of the block was submerged, right? So now we have buoyancy force. So now we have one equation and one unknown, which is just FA, which is what we're trying to solve for. So we can plug in buoyancy force and weight force, and then we can solve for what our applied force is, right? So when we do that, we get that our applied force is 0.012 newtons, and that is in the upward direction as we've drawn in our picture. All right, so last but not least, we have our pre-lab practice problem number 6. What force must be applied to the block to have the block be completely submerged? State both the magnitude and the direction of the force. So now our y equation, when we sum up our forces in the y direction, is going to be a little bit different, right? Because this time our entire block is submerged, and we know that in the equilibrium scenario, where we're not applying a force, only 3.6 centimeters are being submerged. So now we're pushing down on the block to get the additional 2.4 centimeters submerged under the surface of the water. So that means our applied force is going to be downward, right? But we've defined up as positive, so when we sum up our forces in the y direction, we have our buoyancy force is positive, but our applied force is negative, and our weight force is also negative. Once again, we have one equation and 2 unknowns, which is bad, but thankfully we have another equation to solve for one of our unknowns, the buoyancy force. And in this case, the buoyancy force is going to be greater than our equilibrium scenario. So we expect to get a number greater than 0.07 newtons. If we don't, we might want to check our math because that's logically what makes sense. So when we calculate our buoyancy force this time, it's the same equation, so we have the density of our fluid times the cross-sectional area of our object times the depth that the object is submerged, which this time is the entire height of this object, because the entire thing is being submerged when we apply this force, times gravity, right? And this is equal to our density of our fluid, right, which is 1,000 kilograms per meters cubed, times our cross-sectional area, which is 0.011 meters times 0.018 meters, right, because our length and our width, our cross-sectional area has not changed. What has changed, though, is this is our entire height now, because the entire depth of the object, or the entire height of the object, is being submerged. So that full 0.06 meters or 6 centimeters is being submerged. So we use 0.06, and then we're going to multiply by gravity, right? 9.8 meters per second squared, and we get 0.116 newtons, which is what we would expect. It is larger than our equilibrium scenario, where some of our block is not submerged, right? So our buoyancy force wouldn't be as great because not as much fluid is being displaced. Okay, so now that we know our buoyancy force, then the only unknown here is our applied force, which is what we're trying to solve for, right? So we can just plug in our buoyancy force and our weight force and then solve for our applied force. So when we do that, we get that our applied force is 0.046 newtons, and that is in the downward direction as we've drawn in our figure. All right, so that's it on pre-lab practice problems for lab number 8, but if you would like to stay tuned, I'm going to go through some lab 7 review problems, because as you know, the quiz will have 5 questions from last week, so lab 7 friction, and 5 questions from this week, so lab 8 buoyancy. So some review. Say we have this picture, so this should look pretty familiar, right? This is how we set up part 2 for the friction lab last week. So we're given some information. We're told that mu k is 0.2. We're told that the mass of this hanging mass is 250 grams or 0.25 kilograms. And we're told the mass of this block resting on the surface is 450 grams or 0.45 kilograms. And we want to calculate several things, such as what is the normal force, so that's right here, what is the force of kinetic friction, Fk, what is the acceleration of the system, when the system is accelerating, what is the tension force, so we can calculate it here, we can calculate it here, I'm going to do it both ways, and then what would the tension force be if the system were not accelerating, so we'll talk about if there were no acceleration, how would the tension force be different. So the first thing that we want to know is what is the normal force, or capital F subscript capital N. So the normal force for a horizontal surface is pretty simple. Remember that only the mass of the block is contributing to this normal force because only the mass of the block is resting on a surface. The normal force is the force that is equal and opposite to the weight force that a surface feels. So therefore, this hanging mass over here has absolutely nothing to do with the normal force because it is not resting on a surface. Therefore, it does not have any normal force associated with it, right? So when we sum up our forces in the y direction, we have our normal force going upwards, so that's positive, and we have our weight force of our block going downwards, so that's negative, and this is equal to 0. And the reason for that is because we have no net acceleration in the vertical. You'll just have to take my word for it since we're not viewing it as a system just yet. You may be looking at this acceleration and feeling a little bit skeptical, but I can promise you that this block is not bouncing around up and down up here, and so therefore we know that there is no net acceleration in the vertical here. It is only being dragged to the side by this hanging mass that is plummeting downward, connected by a string to this block, right? Therefore, we know that we are multiplying the total mass of the system by an acceleration of 0. Okay, so that means our normal force is equal to the weight force of our block, so 0.45 kilograms times 9.8 meters per second squared. That means our normal force is 4.41 newtons. Moving on to our second question, what is the force of kinetic friction? So F subscript K. Fk is equal to mu k times the normal force. Well, we just solved for the normal force and we were given mu k, right? So it's just 0.2 times 4.41 newtons, and that gives us 0.882 newtons. And that is our Fk, or our force of kinetic friction. What is the acceleration of the system? So A over here in this scenario. So if we view this as a system, if we eliminate this string and our tension forces, because we know that our tension forces are going to cancel with one another, and that this string is run over a massless, frictionless pulley, but inextricably links these two masses so that they're just one unit, then we end up with a view like this. We have the mass of our block and the mass of our hanger. The mass of the hanger times gravity is the force that is driving the system and generating this acceleration. And the only thing that's opposing it is our kinetic frictional force. Okay? So we can solve for our acceleration by computing the net force on the system in the x direction, and we set it equal to the mass of the system times the unknown acceleration. So here we have, when we sum up our forces in the x direction, we have the mass of the hanger times gravity minus our frictional force, right, because they're opposing one another, and the acceleration direction is our positive direction. And this is equal to the total mass of the system times the acceleration. So now we plug in the values that we know. So we have 0.25 kilograms, that's the mass of our hanger, times gravity, 9.8 meters per second squared. We subtract Fk, which we calculated to be 0.0882 newtons, and then we set that equal to the total mass of the system, so the mass of the block, which is 0.25, or sorry, this is actually backwards, 0.45, and this would be 0.25, right? But same, right? Mass of the block, 0.45, mass of hanger, 0.25, times the acceleration, which is what we're solving for. So once we simplify this, we get 2.4 newtons, 2.45 newtons minus 0.882 newtons, and that's equal to 0.7 kilograms once we simplified this. So then if we difference these two values, we get 1.568 newtons is equal to 0.7 kilograms times the acceleration, and this is equal to 1.568 divided by 0.7, right? We want to divide both sides by 0.7 kilograms so that we can get acceleration by itself. And once we do that, we get that acceleration is equal to 2.24 meters per second squared. All right. So when the system is accelerating, what is the tension force on MB? So as I mentioned, we're going to find the tension force using MB, and we're going to find the tension force using MH. And then we're going to compare them to confirm what we already know, right? So here's our free body diagram for the mass of our block. So we have the normal force and the weight force, which we established cancel out, so we're not going to focus on that. But then in the x direction, we have our kinetic frictional force and our tension B. Okay, so if we are defining our acceleration direction as our positive direction, that means our tension force minus our frictional force is equal to, remember, the mass of the block, because now we're doing an internal force, so we just want to focus on the one object that we're talking about. So mass of the block times the acceleration. So now I just drop my sum of forces in the x direction, and I'm going to rearrange to solve for what I'm looking for, right, which is the tension force on MB. So when I rearrange this equation, I get that the tension force on MB is equal to the frictional force plus MB times the acceleration, right? All I did was I took this Fk and I moved it to the other side, so they add together, right? Then when we plug in our values, we have 0.882 newtons, which is our Fk, and we have 0.45 kilograms, which is MB, times 2.24 meters per second squared, which is our acceleration. When we add those two values together, we get the tension on mass B is equal to 1.89 newtons. All right, so then if we do the same thing for the tension force on the hanging mass, so in this case, if we draw our free body diagram, we have the tension force on the hanging mass going upwards and the weight force of the hanging mass going downwards. That's actually what's driving all the movement of the system. Our acceleration is in that direction, so that's the direction we're defining as positive. So when we sum up our forces in the y direction, we end up with mh times g minus th, right, because this is in the positive direction, this is the negative direction. This is equal to mh, remember, because we're doing internal forces, so we're focusing on that one mass, the hanging mass this time, times the acceleration of the system, right, because they are accelerating. If we rearrange this equation to solve for th, which is what we're looking for. We get the TH is equal to MH times G, right? All we've done is we've moved to the TH to this side of the equal sign, and then moved this MH times A to this side. So TH is equal to MH times G minus MH times A. And then when we plug in our known values, so MH times G is 2.45 newtons minus MH times A, so 0.25 kilograms, that's the mass of our hanger, times 2.24 meters per second squared, that's the acceleration with which this system is moving. So then we get that TH is equal to 2.45 minus 0.56, and we get that TH is exactly the same thing. We get 1.89 newtons. And just to remind you, if this drawing is messing you up a little bit because they're at 90 degrees from one another, remember that we can view the system this way. We can eliminate that massless, frictionless pulley, right? And we can look at it as here is our mass of our block, here is our hanging mass, and here are our tension forces. So here's TB, here's TH. TB is to the right at a force of 1.89 newtons, and TH is to the left at 1.89 newtons. So they're essentially a resultant neutralizer pair. They're equal in magnitude but opposite in direction. They cancel out, right? They have absolutely no impact on the external forces of the system whatsoever because they are inextricably linked by this string. They are part of the same system. So no matter, even if we define them like as being different masses outside of the system, they are still connected. And so they cannot impact the external forces, which are MHG and FK. So just remember that. All right, so last but not least, we want to say that the mass of our block is not moving such that it needs to be tapped to move, and then it moves with no acceleration. So what would the tension force be? So what we're getting at here is if we had no acceleration to our system, what would our tension force be? How would it change? Okay, so the first thing that we're going to do is we are going to look at our system as a system, and now, for us to have no acceleration, yes, it could be stationary or it could be moving. And so it really won't change what the tension force is, whether it's moving or if it's stationary, because there will be zero acceleration either way. But just for simplicity, so that we're only working with one F term, I'm going to say that it's moving, so it's moving with a constant velocity. That way we're working with Fk, and we don't have to worry about working with Fs max. That'll get confusing using multiple terms. Okay, so when we look at our system view, we have our hanging mass, we have the mass of our block that's on the surface, and what's driving this system would be the hanging mass times gravity, and then what would be opposing it would be the frictional force. Now, in our scenario before, we did have an acceleration, but in this case, we're saying that we have no acceleration and we have to tap it to move. So if you want to think about it as maybe this is a stickier surface that we're working with now, that's fine. What we're just getting at is how would the tension force change if the acceleration is equal to 0. That also does mean that our frictional force is going to change, right? Because if we're not accelerating, that means we have a greater force that must be opposing the motion, right? So we can see that down here, right? If we sum up our forces in the x direction, we have our hanging mass times gravity minus our frictional force is equal to the total mass of the system times the acceleration. And so when we plug in these values, mh times g is 2.45 newtons minus fk. This is going to be a new value, a bigger value than we had before. Remember, that was the 0.882 newtons, right? So this is going to be a bigger value now that we have to tap it to get the system moving. So we're solving for that first. So we have the total mass of the system here, and then this is times 0, right? Because we've established that the acceleration is equal to 0. So in this scenario, our kinetic frictional force is equal to 2.45 newtons, which is exactly the force that is making this system go. And this really shouldn't come as a surprise, right? Because if we have no acceleration, that means there's no net force. That means this frictional force is balancing this driving force, right? So then if we come over here and we look at our free body diagram for our block that's resting on the surface, of course we've established that in the y direction our forces cancel, right? So our normal force and our weight force cancel. But in the x direction we have Fk, which is now 2.45 newtons, and we have our tension force, right? So we're going to set up our forces just like we did a couple slides ago, right? Where we were looking at this guy, right? So we're going to set up our forces the same way, but now we're using a different Fk value, okay? So we rearrange our equation to solve for Tb because that's what we're interested in. We want to know what the tension force is going to be now that we have no net acceleration. So Tb is equal to Fk plus mb times the acceleration, right? All we did is we moved our Fk over here and added it, right? So we add these two together. Essentially, this term here is going to go to 0, right, because the acceleration is equal to 0, so it doesn't matter what you multiply it by, the mass of the block, 0.45 kilograms. So we're just left with Fk. So that means that the tension force on the block that's on the surface is equal to Fk, right? And you can see that right here, right? Fk plus 0. So tension force is equal to Fk, which is equal to 2.45 newtons. So when the system is not accelerating, there is going to be a greater tension in the string. Now over here, if we look at our hanging mass, it should really come as no surprise. I'm sure you've probably jumped down and saw that our answer is the same, right? Internal forces, they're going to balance. But when we look at our hanging mass, we have our tension force going up, we have our weight force going down. This is the direction of our acceleration, so I'm going to define that as positive. So we sum up our forces in the y direction, just like we did on this slide here, right? And we end up rearranging our equation, right? Because we're trying to solve for the tension force for the hanging mass, right? So when we rearrange this equation, we move our tension force over here, we move mh times a over here. So then we're left with mh times g minus mh times a. And when we plug in our values, we have 2.45, which is mhg, minus 0.25 kilograms, which is mh, times a, which is 0. So we have 2.45 minus 0. So once again, we get the tension for the hanging mass, as I mentioned before, is 2.45 newtons. And if we remember to look back at our drawing here, we know that these are equal in magnitude and opposite in direction. And then because we're talking about a situation where the acceleration is 0, these two forces balance each other out, but still these tension forces are not impacting the external forces at all. Okay, and then one last thing before I go. Let's just say that mu k was not given. So up here, yeah, we were given it. It was 0.2. But in this situation, I mean, I think it's sort of implied that this would be a stickier surface, right? Because there's more friction. So let's just say that we wanted to calculate mu k for this new stickier surface, okay? And let's say that, you know, our normal force is still the same. The mass of our block hasn't changed. It's still a horizontal surface. So the normal force is still 4.41 newtons. So how would we go about finding mu k? Well, we know Fk is equal to mu k times the normal force, right? And so we solve for Fk over here, and we know that the normal force is 4.41, so we just rearrange this equation to solve for what we want to know, which is mu k. So we have Fk divided by the normal force is equal to mu k, so that's just 2.45 newtons divided by 4.41 newtons, and that gives us 0.56. So that would be our new mu k value. Well, hopefully you found this pre-lab helpful, and best of luck on quiz 8.